Hello friends, let's resume our lecture on understanding a typical creep curve. So in the previous lecture we saw that when we want to define or describe the behavior of a material during a creep test, we need to consider both the mechanical condition that you impose on the material, that is the stress, and the response of the material to the imposed mechanical condition, that is strain, and the characteristic description of the creep, which is the time dependent behavior of the material and therefore time. Now when you want to study both the behavior of the material under different mechanical condition over a period of time, then you would need a three-dimensional plot. So in order to make this easy for us, in order to understand it, make it more understandable, more approachable rather, we assumed one of these to be a constant. So the time cannot be assumed to be constant because it is the characteristic description of we cannot move away from the characteristic description of the creep. So we are allowed to assume one of these two that describe an usual or a conventional mechanical testing, that is stress and strain, to be, we can assume one of these to be constant. And in the previous lecture we assumed that the mechanical condition that we impose to be constant. Now it is important to note that since this mechanical condition is assumed to be constant, the mechanical condition that we are talking about should not vary to all through the period of testing. Even though there might be the change in the dimension of the material during testing, the mechanical condition that we impose, that is the stress, should not vary all through the period of testing. So appropriately we have to ensure that the stress that we impose is constant. So once you have ensured that the stress is constant, the stress or the mechanical condition that we impose on the material is constant, then it becomes rather consistent for us to represent the creep behavior in two dimension. So to represent the creep behavior in two dimension, we have to ensure that the stress that we impose on the material is constant all through the test. So once you have ensured that, then you can treat or you can represent the behavior of the material or the response of the material to the given mechanical condition over a period of time that characterizes the creep in this manner, wherein you would consider time in the x-axis and the strain, which is not elastic or plastic, it is the creep strain in the y-axis. Now we saw in the previous lecture, in a crystalline material, a characteristic or rather a representative creep curve would look something like this. It has an instantaneous creep region followed by a region where the creep rate gradually decreases, and after this instantaneous and the gradual decrease in creep rate, when I talk about creep rate, you can relate it to the slope of this curve, and immediately following this decrease or the decelerating slope or decelerating creep rate is again, it is this nothing, this is the rate of change in the strain, which is nothing but the slope of the curve. Immediately following this decelerating creep region, which we also refer to as the transient region, we have a region wherein there is just a marginal change in the strain or creep. So there is over a period of time there is only a marginal change in the creep or the strain, and this we classified or categorized into second stage, and we also refer to it as the steady state creep region. And immediately following the steady state creep region, there is an increase or tremendous or significant increase in the rate of strain, and that means there is an accelerating creep which ultimately leads to the failure of the material. So this is what we previously saw in the previous lecture, how we can categorize a typical creep curve. So what we have, if you want to show the categorization in this plot, we have our instantaneous creep region, which is then followed by a decelerating creep region or a transient creep region, because the transient, the name transient means it connects the instantaneous with the steady state creep region. And we have the steady state creep, which is characterized by not much change in the slope of the curve, or rather a region where the strain almost remains constant. And finally you have your accelerating creep, which ultimately leads to the failure of the material. So in the previous lecture we categorized these two, that is the instantaneous creep and the transient creep as stage 1. The steady state creep, we categorized it as stage 2. And finally, the accelerating creep, we categorized it as stage 3. The reason we were able to categorize these into stage 1, stage 2, stage 3 is because they occur like one after the other. They occur sequentially, and that's the reason over a period of time, and that's the reason we were able to categorize that as stage 1, stage 2 and stage 3. We saw one of the reasons for categorizing the overall creep curve into these different stages is because in generally the changes in the material that are responsible for each of these stages are different. And so if you want to study this creep behavior in relation to that of the material changes, then we can relate each of these stages to the material changes, and then it is easy for us to understand what changes brings about this particular stage in creep. So for our understanding, we have categorized this overall creep curve into different stages so that we can relate the changes in the material that cause the particular creep stage, that is responsible for the particular creep stage. So in order to have a clear theoretical understanding of the theoretical factors that govern each of these stages, we have split the overall creep curve into different sections, and this approach we refer to that as phenomenology. Now, even though we have defined, or we have stated that there are 3 stages, and we have categorized the first 2 into 1, and the other 2 we have left them or categorized them separately into 2 and 3 stages, we have to be very much clear that we are acquainted with all the different all the terminologies that are used to categorize this creep curve. Meaning, so far what we have done is we have just coupled first two aspects of the creep curve which have different slopes into stage 1, and the second aspect of the creep curve or section of the creep curve which has its own which has its own characteristic slope as stage 2, and the third section of the creep curve which has a different form of slope or which adapts a different trend as stage 3. Now, this is one of the ways of categorizing the creep curve. This is just one of the ways of distinguishing the creep curve. The reason is because the reason why I say that it is just the one of the way is because in this creep curve we have a region called instantaneous creep region. So this region here, let me make it even more darker. This region here is the instantaneous creep region. Now, this instantaneous creep region is brought about in this curve by the load that you impose in this system. So, unlike tensile loading, wherein your load will gradually increase with the strain, in creep you suddenly impose the load, and the immediate change in the strain is shown by this instantaneous creep. Now, the time taken for this instantaneous creep or this sudden strain exhibited by the material to the sudden imposition of the load, let us assume that to be Tin. Now, there is an overall period of time during which the material behaves and the material evolves and ultimately fails. So, for a given loading condition, for over a period of time, the material evolves and ultimately fails at a particular temperature, and this overall time taken, let us refer to that as Tc. So now we have considered two characteristic time period. The first time period, that is Tin, is confined or it characterizes the instantaneous strain or the period over which the material exhibits an instantaneous strain, and Tc is the overall time taken for a creep testing of the material. So overall time, the creep behavior is exhibited by the material till it fails. So the overall time taken for the testing is given by Tc, and the time taken for the instantaneous creep is referred to as the Tin. Now, when you split the overall time, when you split the time dependent behavior or the time taken for the material to fail under a given creep condition into Tin, that is time that is restricted to the instantaneous creep, and the overall time taken for the creep testing, that is Tc, and if we are able to represent in the same plot with T representing or with X axis representing the time, it means that when you compare Tin with Tc, both these are of the same order. Both these are of they are not in the overall context of the time, in the overall time taken for the creep. When you include Tin in the representative creep curve, when the change in the material or the creep behavior within the time Tin is included in the creep curve, then it means that the order of Tin is something similar to that of the Tc. To put it simply, Tin is not insignificant when compared to Tc. So when your initial instantaneous strain or the time taken for the instantaneous strain, it is not negligible when you compare to the overall time taken for the creep. Only then you would be able to show this region in the representative creep curve. When you include then this instantaneous creep region, then your stage 1 will comprise of instantaneous and transient creep region. So there is a condition that needs to be satisfied when your creep curve should be of this form. So that condition is the time taken for the instantaneous creep should be relatable to that of the overall time taken for the overall creep behavior or the overall creep testing. Only when your time taken for the instantaneous creep is relatable to that of the overall creep duration, only then you will be able to include this instantaneous creep region here, and only then your stage 1 will comprise of the instantaneous creep region and the transient creep region. Now, what if the time taken for the instantaneous creep is very much less than the overall creep testing time or the overall duration over which the material survives before it fails? What if this condition prevails in a crystalline material? So under this condition, the creep curve would look something like this. Under this condition, when the time taken for the instantaneous time is significant when you compare to that of the overall creep time. Let me repeat. When in a crystalline system, the duration taken for the instantaneous creep is significant when you compare it to the overall creep period, then it becomes rather difficult for us to express it in terms of this curve. So therefore, the curve begins by the transient region and follows with the steady state region and ultimately the accelerating creep region. Now, when your material or in the material that you are testing, the instantaneous creep or the time taken for the instantaneous creep is totally negligible, is completely negligible, or is of the order several times less than that of the time taken for the overall creep, then you cannot include the instantaneous creep region in this plot, and your curve begins with the transient creep region, and ultimately it follows with the steady state creep region, and finally you have your accelerating creep region. So in that case, your stage 1 will exclusively comprise of the transient state region. So depending on how or the time taken by your material for the instantaneous creep, the description of the stages vary, particularly the description of the stage 1 varies. When the time taken for the instantaneous creep is significant when compared to the overall creep period, then your curve begins with the transient region. Then the stage 1 is exclusively characterize the transient creep, and the other creep regions, that is the steady state, will not change. The steady state, that is the stage 2 of the creep, will be the same, and similarly the stage 3 of the accelerating or the ternary creep will be the same. However, one factor that changes is the stage 1 of the creep. Here, when your time taken for the instantaneous creep is relatable to that of the overall time, then the stage 1 would include both instantaneous creep and transient creep. But if the times taken is insignificant when you compare it to the overall time period, then your stage 1 will exclusively comprise of the transient creep. So this is something you need to understand, and depending on the plot that you see or the creep plot that is before you, you need to understand, or you need to appropriately define the stage 1 of it. Supposing if the plot before you comprises of or includes the instantaneous creep section, then your stage 1 should comprise of instantaneous creep and the transient creep. If the plot before you begins with the transient creep alone, then your stage 1 should exclusively be defined by the transient creep. Now this is because it all depends on the time taken by the material to complete the instantaneous creep. If you have a crystalline material that takes a definite period of time that is relatable to the overall creep testing, then your stage 1 of that material would include both instantaneous creep and the transient creep. If not, if the in some material, if the instantaneous creep is, as its name suggests, is very instantaneous, or rather the time taken for the instantaneous creep is very much negligible to the overall creep period, then your stage 1 or the overall creep curve will begin with the instantaneous creep, or rather transient creep, and then your stage 1 should exclusively be defined as exclusively be categorized by the decelerating creep or the transient creep. Now the other way of making it more generalized, so if you look into Professor Dieter's book, he would say that the British way of looking into the creep curve, so the very general way of defining the creep curve would be by considering all these, by taking into the consideration of the influence of the instantaneous time on the influence of instantaneous time, or the time that is required for this instantaneous creep on categorizing the different stages. If you want to get rid of that, the influence of TIN, that is time taken for the influence of the instantaneous creep on categorization of the creep curve, if you want to get rid of that, then the easier way of doing it is treating the creep curve as a 4-staged one. So instead of 3-staged one, you can treat that as a 4-staged one, wherein the initial stage would be, the first stage would be the time or the instantaneous creep, the second stage would be the transient creep, and the third stage would be the steady state creep, and the final stage would be the accelerating creep. So instead of having 3 stages, if you want to have a more generalized representation of the creep, when you want to have a creep curve that is independent of the time taken for the instantaneous creep, then the easier way the way to achieve it is by splitting the curve into 4 stages, and the first stage in that case would be the instantaneous creep. The second stage would then be, let's use the green here, the transient creep, and the third stage in that case would be the steady state creep, and the final stage would be the accelerating or the ternary creep. So what we have done is, or like Professor Dieter says, the British way of looking at this curve is, we can now distinguish the creep curve into 4 sections, and supposing your material is so instantaneous that you don't have the transient creep region, or rather, pardon me, the instantaneous creep region, then you can say that one of the stages is absent and you have all the other stages. So instead of defining your creep curve, or instead of categorizing your creep curve based on the time taken for the instantaneous creep, when you split the curve into 4 different stages, you can quantify or you can describe each of these stages based on time taken for the material for each of these stages. And if the TIN is so low and it is close to 0, then you can say that the stage 1 of the 4-stage creep curve is insignificant. So this is a more generalized way of looking at things. So if you want to recollect, or if you want to give a gist of this separation of stages, when you categorize the overall creep curve into 3 stages, then it becomes, or it is dependent on time taken for the instantaneous creep. Now when your instantaneous creep is more or less relatable to that of the overall time taken for the creep, when your instantaneous creep is not less than, when it is not very much less than the overall time taken for the creep, then the stage 1 is the combination of instantaneous creep and transient creep. So when your time taken for the instantaneous change is relatable to that of the overall creep time, then the stage 1 would be the combination of instantaneous creep and the transient creep. If on the other hand, the TIN rather is very much insignificant or very much low, very much low when you compare to that of the overall time taken for the creep, then your stage 1 will exclusively comprise of the transient region alone. So if you want to get rid of the influence that the time taken for the instantaneous creep has on the categorization of the creep curve, the easier way to do it, or the British way to do it, is representing the creep curve categorizing the creep curve into 4 stages. So ultimately what you have is a 4-stage creep curve, and when you want to say that the material is so instantaneous that the time taken for the instantaneous creep is slow, very much insignificant compared to the overall creep time, then you could very well say that the stage 1 is rather correspondingly not much significant, and it is not represented in the curve. So these are the different ways of representing or categorizing the creep curve, and we have seen that this helps us to relate to the material behavior that brings about these different stages during the creep. Now let us get back to our representative creep curve, and let us see how we have so far categorized it. So without knowing much of the theoretical background, we were able to categorize the creep curve so far. We were able to categorize into 3 stages, and we were able to categorize into 4 stages without knowing much about what is the material change that is responsible for each of these different stages. So far we have not talked anything about the material aspect of things. We have just looked into the curve. It was just by looking into the curve, by just talking about the nature of the curve in different regions, we were able to categorize into different stages. And let us talk something about what enabled us to categorize this curve into different stages. So we did not talk much about any material aspect so far. We just saw the creep curve, the nature of it, and we categorized it. So what made us, or what aided us in categorizing this curve, is what we will focus on. So what we have is, again, an instantaneous creep region, a transient creep region, and a steady state creep region, and an accelerating creep region. So we have our strain and we have our time. So now the reason or the factor that helped us to categorize this overall creep into different stages without knowing or without considering much about the material factors that are responsible for this behavior is the slope of the curve. And the slope of the curve, the way we can define the slope of the curve is nothing but this, and this is nothing but the creep strain rate or the creep rate. So in each of these sections, they have their own characteristic slope. So the only difference, or the only way we were able to characterize each of these sections were based on the slope, and these slopes we referred, or we can quantify them, or we can refer to them by considering what is there in the y-axis as the creep strain rate or the creep rate. Now in the earlier stages, or in the instantaneous, during the instantaneous stage, the creep rate or the slope is rather constant. As you can see, it is more or less straight, and it is and therefore we can assume that the creep rate is constant. It is depending on, like we saw in the previous description or the categorization of the creep curve. This section is again dependent on the material. It can be the instantaneous creep can occur within a very small period of time, thereby allowing us to get rid of it, or it can occur over a period of time. But irrespective of how it occurs, it is rather instantaneous. It occurs rather immediately after you apply the load, and during this period, this creep strain is rather constant. And now, when we look at the transient region, when I say the creep strain is constant, I mean that creep strain rate or the slope is constant during the instantaneous creep. And when you talk about the transient creep region, we also refer to that as the decelerating creep, because the slope in this section of the creep curve is decreasing. That means the strain rate in this section of the curve is decreasing. And after this stage, that is after the transient creep, we have our steady state creep. In this state or in this section of the curve, the slope of the curve is more or less constant. There is no drastic change in the creep rate, or there is no drastic change in the slope. It is more or less constant. And finally, in the tertiary stage of the creep, there is a sudden increase in the slope, or the strain rate, the creep strain rate suddenly increases. It is an accelerating creep. That's why we refer to it as the accelerating creep. Now let us try to graphically represent how it looks like. So let us try to graphically represent how the creep rate or the creep strain rate changes over the period of time during our creep testing. Because this is using this, we were able to categorize the different stages of the creep. Using the creep strain rate, we categorize the different stages of creep. Now let us see how one can graphically represent this slope or this creep rate of the curve. Now for that, let us assume this to be the y-axis, and let us treat the time as the x-axis for now. Now as you can see, during the instantaneous creep, the slope is constant, and this instantaneous creep region is not so significant, or it depends on the material. It often is not significant when you consider the overall period of time, the overall creep period. So overall duration over which the creep occurs. So it can just be represented by a small region wherein you have your constant strain rate. And now this is followed by the transient region, which is predominant, and this transient region is characterized by a decrease in the creep rate. So this is how the transient region can be represented with respect to time and the creep rate. So there is a significant decrease in the slope of the curve, and that is there is a significant decrease in the creep rate. And this transient region is followed by a region of steady state creep wherein the rate is more or less constant. And finally, you have your accelerating creep region, which is characterized by an increase in the slope, meaning there is an increase in the creep rate. So similar to that of the creep curve, wherein you had 3 or 4 stages depending on which approach you follow, we also can categorize, or we can also section this overall curve into different stages, meaning there can be stage 1, 2, 3 and 4, or we can combine these two, and because this depends or this varies with the material, so we can combine these two and treat this as stage 1. So this combines instantaneous and transient creep region, so that is the stage 1. And here we have plotted the slope that has helped us to categorize the creep curve, and there is also a similar reflection in the slope of the curve over the period of time. So how the slope varied, this is rather natural, because based on the slope only we were able to categorize or section the overall creep curve. And when you plot it, when you give a graphical representation to the slope, that is the creep strain rate over the period of time, the stages are completely visible in this plot as well. And here, as you can see, instead of the region 1 comprises of 2 sections: the instantaneous creep region, wherein the slope or the creep rate is constant, which is followed by the transient creep region, which is decrease in the creep rate, or characterized by the decrease in the creep rate. And we have stage 2, so this would be our stage 1, which is expressed in terms of the slope of the creep or the creep strain rate. And we have our stage 2, wherein there is not much change in the slope, or the slope remains more or less constant. And finally, we have our tertiary creep, wherein there is an increase in the slope of the curve, or the creep rate tremendously increases. So this is a way of presenting or illustrating the slope that helped us in categorizing the different stages of the creep. The slope or the creep rate which is characteristic or which characterizes each of these creep stages. They can be plotted in this manner, and they can be categorized into separate stages depending on the material, meaning if your material is instantaneous, meaning the time taken for the instantaneous strain is quite low, then you will not have much of this stage or much of this constant region here, and ultimately your stage 1 will be the transient creep, or wherein the creep rate is gradually decreasing, and the second stage would be exclusively steady state creep, wherein the creep rate is more or less constant, and finally the third region would be an accelerating creep, wherein the creep rate is continuously increasing. So this is the reflection of the slope, or the illustration that shows the reflection of the slopes, or how the slopes or the creep rate would change. Whenever we say slope, it is nothing but in the context of the figure, it is, or in the context of the creep curve, it is the creep rate, how the creep rate changes over the period of, or over the duration of the creep testing. As you can see, the initial stages is categorized by a gradual decrease in the creep rate, and there is a constant creep rate followed by an accelerating creep rate. So what we have so far done is we have given different categorization for the creep curve, and we have looked into the factor that enables us to section the creep curve, and we have plotted it separately. So we have seen that over a period, over the overall duration of the creep, the strain changes over the time, and not only the strain but the rate of the strain also changes. Because this rate of the strain changes, we were able to section the overall creep curve into different regions or different stages. Had been there is no change in the strain rate or creep rate, then we will not be able to section the overall creep curve. However, in a representative crystalline material, there is a significant change in the creep rate or the slope over during the creep testing. We were able to section it, and the nature of the change in the creep curve or the creep rate over the period of time, how the creep rate changes over the period of time, we were able to illustrate that by just considering the creep curve. By just considering this creep curve here, based on this creep curve here, we were able to illustrate how the creep rate changes or how the strain rate changes during the duration of the overall creep. Now, what we have in the x-axis of this creep is the time. So we have considered, given that the creep is defined as the time dependent behavior of the material in the x-axis. So far what we have considered is time, and this is rather accurate because over the period of time during the material response to the given conditions, there is a significant change in the rate of the response of the material, the rate of the strain that the material exhibits, and that is what we have shown here, and that is what helps us to section the overall creep curve. So there is nothing rather inaccurate in using the time here, or when you talk exclusively in terms of creep alone, then time is the most accurate factor that you can consider in the x-axis. Now we have moved away from the creep curve. Now we are talking in terms of the creep rate. We are talking in terms of the overall behavior of the material alone during a particular duration. When I talk about a particular duration, it means that I have fixed my duration. So when I talked in the previous discussions about TC, this is the overall duration of time during which we see the creep behavior of the material, and at the end of this TC, the material would fail. So instead of talking about rather a variable T, since we are focused on a particular material, this particular material will fail at a specific time. We are then talking about a characteristic time TC. Let me repeat. Now when we began our discussion on creep, we defined creep as a time dependent behavior. So we had time in the x-axis, and we represented the behavior of the material in the form of strain over a period of time. Now for present argument, let us make a definite restriction in this time. This definite restriction is that we are not taking the overall time till the kingdom come. No, we are talking about a definite period of time over which at which the material fails. So whatever changes that we are studying is between time 0 to time Tc. The time Tc is the time when the material ultimately fails or the creep test ends. So when we are talking about a specific material and a specific region or a specific duration of time. We are not talking the overall T as a variable, but we are talking in terms of a specific duration of creep testing. So that means that we are talking about from T0 to Tc. We have confined ourselves to T0 to Tc. This Tc, of course, it varies with different materials, but since we are considering now now for this discussion, let us stick to one particular material. Then for one particular material, Tc will be a characteristic time, assuming that your temperature is constant and your stress is constant. When you assume these two is constant, then Tc will be a characteristic property of the material, and we will confine our discussion from henceforth to this Tc. Now when you do that, when you restrict your duration is well known, you have studied the creep of the material, you have understood at what time it fails. So the time Tc is well known to us. Now you want to further probe, further into the behavior of the material in addition to the strain, the overall strain. Now that you know, because you have completely studied you have completely looked into the material behavior over the period of Tc. Now you know how the material responds. Now you know what the strain rate of the strain the material exhibits during the time Tc. Now since you have already known this, you want to probe further and you want to talk about the rate of strain, that is the slope of the curve. When you want to do that, now that you have already defined you are already restricted, you have found a definite time period, it is also permissible for us to represent a different or to consider a different factor in the y-axis. Let me repeat, now that we have studied the overall creep of a material and we have determined that there is a definite period of time after which the material fails, there is no longer creep behavior. So there is a definite creep duration over which we want to study the behavior of the material for a constant stress and a constant temperature. You have already, these all factors are known to you, and you have known the strain the material exhibits during the duration of creep. These all are known to you. Now you want to probe further, you want to look into the rate at which the strain is happening. You want to understand, you want to categorize the curve into, or more fastidiously, you want to categorize the stages of the creep. So for that you are looking into the strain rate. Now when all these factors satisfy, it becomes permissible for you to replace this time here in the x-axis with the strain. So this strain, the time here in the x-axis can be replaced by epsilon OV, which is the overall strain. So you can replace this once you are very much sure about the overall time duration taken for the creep behavior, the overall time duration that is required for the material to fail. Once you are sure about it, and once you hold your load to be constant and your temperature to be constant, then you can represent this change in the strain rate with respect to the overall strain. You can replace the time in the x-axis with the overall strain. Now even if you do that, if you replace this strain with this time here, and you replace this time here, and you replace this with the overall strain, what do you think would happen to the nature of the curve that you see here? How do you think this curve would behave? Will there be any significant change in this nature of this curve? If you think about it, there will not be significant change in the nature of the curve. The only thing that would change is the value that you considered in the x-axis, but the overall trend that you see, the initial instantaneous creep exhibiting a constant slope, that is a constant strain rate, the transient creep exhibiting a decelerating slope or a decelerating strain rate, the steady state creep characterized by a more or less constant slope or more or less constant strain rate, and finally the tertiary section or the tertiary stage characterized by a sudden increase in the slope or a accelerating creep. This trend, irrespective of what you take in the x-axis, will not change. However, since we have already looked into the overall creep curve, since we were able to understand or quantify the time taken for the creep initially, and only after doing that you will be able to plot the rate curve or the strain rate curve. Since we have already been able to understand or quantify the overall duration for the creep, this allows us to replace the time with the overall strain. And when you replace the time with the overall strain, what it helps us is to relate the behavior of the material with the slope of the material. Now, when you see a definite duration or a definite strain exhibited by a material, and when you can relate it to the you will be able to calculate this definite strain in terms of the strain rate or period during which this definite strain has happened, and you can then based on it calculate the strain rate. And when you are able to do that, then you will be able to plot this slope curve irrespective or without the initial strain versus T curve or the initial creep curve. So what I mean by that is, now when you are studying the rate of creep with respect to the overall strain, you will be able to relate the particular strain with the time taken for that strain. And when you are able to relate the strain to that of its time taken, then ultimately what you are doing is calculating the rate of strain. Now, when you plot it without any prior experience, without any prior knowledge about the creep curve, when you plot the particular strain or the time taken for a particular strain with the overall strain, you are considering the overall strain and you are plotting the time taken for a definite section of the strain, and ultimately what you are then plotting is the change in the creep strain rate, because ultimately you are studying in the you are studying under the condition of creep. So ultimately what you are doing is, by considering the overall strain in the x-axis and the creep rate, or considering the change in the strain over a definite period of time or over a period of time in the y-axis, you are ultimately plotting the creep rate versus the overall strain curve. And in order to plot that, when you consider the overall strain and the strain over a period of time, or when you relate the strain over a period of time, then you can arrive at this plot which we have seen in the earlier section. You can arrive at this plot wherein you have your stage 1, stage 2 and stage 3, 1, 2 and 3, without the knowledge of the original creep curve. So one way of arriving at this plot, that is the creep strain plot or the creep strain rate plot or the slope plot without the knowledge of the original creep curve, is by considering or by relating the strain to that of the time it has taken. So we have our load that is constant, we have our temperature that is constant, and your material exhibits a definite strain over a definite duration of time. Now you are calculating the amount of strain with respect to the time, and we are plotting it with respect to the overall strain. So you are calculating instantaneous time at each and so you are calculating in this way the small amount of strain at over a small period of time and relating it to the overall strain. So you are calculating, let us for this sake for this discussion, let us assume the instantaneous strain is with respect to a particular time duration, wherein this time duration is very so let's just say this is dt, that is very small, or rather it tends to be 0. So for this dt you are calculating the amount of strain the material has exhibited and you are relating it to the overall strain, and when you do that you will end up with a plot something like this. So this is you have ultimately ended up with this plot by directly looking into the behavior or the creep behavior of the material. You did not arrive at this plot from the creep curve, you have arrived at this plot from by looking into the creep behavior of the material. So this, by treating or by considering the overall strain in the x-axis, allows us to arrive at this creep strain or the creep strain rate plot directly by looking into the behavior of the material. Now if you consider T here and the epsilon here or the strain here, you would have your conventional creep curve, and we saw the way of arriving at this strain rate curve is by considering its slope. Now we have seen that when you consider the overall creep, or when you study the instantaneous strain exhibited by the material for a small duration of time, and then you relate that instantaneous or the small creep exhibited by the material over a period of dt with the overall strain that is exhibited by the material, or the overall creep that is exhibited by the material, then you would be able to directly arrive at a plot something like this. So the bottom line is, when you replace time with the overall creep or the overall strain, then just by looking into the behavior of the material, you will be able to arrive at or plot the creep behavior in the different manner. Like similar to the creep curve, you have your 3 stages here, but as opposed to our previous consideration, we were able to arrive at this plot not from the initial conventional creep curve, but by looking into the instantaneous strain or the small strain exhibited by a material over a very small period of time dt. By looking into that small strain and relating it to the overall strain, we were able to arrive at this representation, which is also reflects the creep behavior of the material. So therefore, in addition to the conventional representation of creep using strain and time, we can also arrive at or can also represent the creep behavior in terms of the strain rate by considering the overall strain. So that is what we have seen in this plot. Now the reason for us to consider the different ways of representing the creep behavior, or the different ways of representing the material or the response of a material under a definite load, under a given time, in a given temperature over a period of time, the reason why we need to do it is because we have several variables for us to consider. Whenever we describe or define a creep curve, even if it is represented in this manner, that is the creep versus time, or even if it is represented in this manner, you are studying the instantaneous creep over when expressing it in terms of the overall creep, thereby ultimately resulting with a representation of this form, irrespective of how you do it. So we have seen 2 ways of representing the creep curve so far. So the first one considers how much the strain occurs over a period of time, and we have plotted, and that is a conventional way of representing creep. It has different stages, and now instead of considering the time in the x-axis, we have considered the overall creep. What we have essentially done is we have studied the small amount of creep the small amount of creep strain that is exhibited by a material during a small period of dt, and then we have plotted that in relation to the overall strain, and we were able to get a plot that is similar, that is something like this, and that also reflected the different stages of creep. Now it is, of course, we were able to arrive at this plot from the conventional creep curve, but we saw that by changing or by considering the overall creep strain, we can independently plot this curve. Now the reason for having different representation of creep is because we are considering several factors while plotting the creep curves or while studying the creep behavior of the material. So far we have assumed the stress to be constant. Now when you want to assume the other factors to be constant, then we need to have an appropriate representation of creep. We need to have the appropriate ways to calculate the creep behavior. For the different ways of expressing or calculating the creep behavior, considering the appropriate x-axis will be helpful. Now when you change the constant factor of represented or of the factor that characterizes the creep study, so far what we have assumed is the mechanical condition that we impose is constant, and you want to change it, then you have to have appropriate ways of calculating the creep behavior. Now without even changing the constant stress, just with the variable strain and time, we saw that you can represent or you can arrive at the creep curve by 2 means. One is by considering the time alone, the other is by considering the overall strain. Even though the y-axis of these creep curves vary and correspondingly the nature of this curve vary, both these curves showed the different stages of the creep behavior. They explicitly or clearly they were able to section the different stages of the creep behavior. Now this would help us to devise other creep testing methods wherein the other factors are assumed to be constant, wherein we are able to, it gives us a lot of room to play around, so that you can assume one factor to be constant and the other factor to be variable. So based on this understanding, let us build and see what are the other ways to study creep in the subsequent lecture. So in the next lecture, we will build on this. We will try to exploit the advantage of considering the overall strain in order to study the creep behavior, and then based on that, we will see how else we can plan a creep test. So in the next lecture, we will be presenting a different depiction, or will be presenting a we want to present a different representation for the creep curve, which is much different from the one that we have seen so far. So the one that we have seen so far includes strain and time. The second one is also fairly derivable from the conventional creep curve. This is because we have the setup so far we have assumed this to be for both these cases more or less similar. The factor that we have assumed to be constant in both these cases is more or less similar. We will try to play around with this factor in the subsequent lecture. So let us see ourselves in the next lecture. Thank you.